we're going to be talking about speed and velocity graphing. We're looking at section 3.1 in your book. Chapter 3 is on motion, acceleration, and forces, and section 3.1 is on describing motion. If you want to follow along with your book, that's on page 70. The important things that you're going to learn here is the difference between distance and displacement, and how to calculate the average speed, as well as explaining the difference between speed and velocity, and looking at motion graphs. So those are the key points that you want to pick out of this podcast, and you'll also find those listed on the top of page 70 as well. Speed is essentially any movement. Okay, it's a movement over a certain amount of time. So movement is usually expressed by the distance traveled. It's also, distance is referred to as displacement, how far you moved from the starting point. So distance and displacement somewhat go hand in hand. Distance tend to be just how far you went. Displacement tends to add in the direction that you went. So you've got distance over and displacement. And speed is essentially how fast you are moving. How much time it took you to go a certain distance is your speed. So we say speed is the distance an object travels per unit of time, like miles per hour or meters per second. How you calculate speed is, it's called the rate. What you're finding is the rate. It's any change over time. And what we're going to be talking about is the distance that you traveled over a certain amount of time. So the distance is your change in position, and the speed is the rate at which you did that, the rate at which you moved that distance. For the sake of science, we usually talk about this in meters per second. We use meters because the rest of the world, except for the United States, looks at things in terms of meters rather than feet, or kilometers rather than miles. We're the only country, or one of only 2 countries, that uses things like feet and miles instead of meters and kilometers. So speed is the formula, distance divided by time, and it's usually calculated in meters per second. If you look here at some common speeds, okay, and their standard unit of measure, that's what SI means. Okay, that's their standard unit of measure. Like a rocket escaping the Earth's atmosphere would be recorded in kilometers per second. A car traveling down the highway would be recorded in kilometers per second. And hopefully you all know that the crust of the Earth is broke up into large plates that move, and those might move at a rate of 2 to 17 centimeters per year. So we can use different units of measurement: kilometers per second, kilometers per hour, centimeters per year, miles per hour, meters per second, feet per second. The key is to remember to label everything, and whatever the distance and the time was in the problem should be the distance and time in your answer, should be in your answer. Now for a reference, I'm a visual learner, kilometers per second. What's a kilometer? A lot of people don't know because we don't use kilometers, we use miles. So basically 1 kilometer is about half a mile. So if I said that something went 100 kilometers, that would roughly be 50 to 55 miles, somewhere right in there. Just to give you a visualization of what a kilometer is in terms of a mile. So 1 kilometer is about half a mile. Usually speed is not constant. Okay, it's very rare that something travels at a constant speed over the entire distance. You think about a runner doing a lap around the track. They're going to have points where they go faster, and they're going to have points where they go slower, and they're going to have points where they travel the same speed. But that entire trip around the track was all different speeds. Think about it like riding a bicycle. Okay, you go to ride a bike. You look at your speed there. You start out taking off on your bike, you're gaining speed. So you're gaining speed, but now you got to go up a hill. So now your speed goes down. Then, so you climbed the hill, and when you climbed the hill, your speed got slower. Now you get to go down the hill and your speed got really fast. Then you had to stop for a street and a red light. No speed. And then you pedaled your bike and reached a constant speed for a while, and then you slowed down again. So over this entire distance, your speed varied. It changed a lot. Going up a hill, down a hill, stopping, starting. So speed is rarely ever constant. So when we calculate speed, distance over time, we're usually talking about an average speed. Okay. So if you went on a trip, okay, let's say you went to visit grandma and she lives in Nebraska, and it was 200 and some miles. It was 210 miles was your total distance. And it took you 3 hours to get there. Okay, distance divided by time. Okay, 210 divided by 3 hours, your average speed is 70 miles per hour. That didn't mean you went 70 miles per hour the entire trip. That was just your average speed. At some point you were going faster, and at some point you were going slower. Average speed is that speed of motion when speed is constantly changing. It's the total distance divided by the total time to give you just an average. And this is an example here. Traveled 5 kilometers in a quarter of an hour, 0.25 hours. The average speed was 20 kilometers per hour. That didn't mean you traveled at that speed the whole time. That just means that was your average speed for the whole trip. Instantaneous speed is that instant speed, that speed at that exact moment. Okay, 1 instant. When you look at a speedometer on a car, that's your instant speed at that moment. That's not your average speed for your whole trip. That's just your speed right at that exact moment. And we refer to that as instantaneous speed. Okay, and there's a little bit of a difference between the two. Average speed versus instantaneous speed. Okay. When something speeds up or slows down, its instantaneous speed changes. If it happens to be traveling at a constant speed, then the instantaneous speed doesn't change. And that happens a lot when you're setting the cruise control on a car. If I set the cruise control at my car at 70 miles per hour, I just sit back and cruise along at 70 for a while. So for a while, I'm going to be going a constant speed. Again, not the entire trip, but for a while, I could be traveling at a constant speed. If we take a look at the graph here, where we're going to graph speed, and there's also one in your book on page 74. Speed is graphed as distance over time, the same formula. Distance here over time. And if we look at this person, take the red line for an example, they started off at a nice steady speed, increasing, really nice steady speed. They covered pretty even distance in a consistent amount of time. Okay. Then here, their distance didn't change. They stayed at this exact distance, which had to mean they were stopped because they weren't covering any more distance. So maybe they were riding their bike and then they stopped for something. Maybe a red light, maybe a car, but they stopped. And maybe they stopped in this situation because they forgot something. Because what happened here? Their distance went back to 0. So, therefore, they went back to the beginning. They went back to their original spot. So, nice steady ride going on. Whoops, I forgot something at home. I turn around and I go back to home again. But they kept a pretty constant speed here. Okay. Here, it was a steady speed, but it was a much faster steady speed. Because they covered 10 meters in only 2 seconds. So that was a faster speed. Where this person here covered 8 meters in 4 seconds. Steady, though, because the lines are going up at this nice even angle. And you can look at that in your book, too. It's the exact same graph, or a similar graph, excuse me. So time is plotted on the horizontal axis down here, and distance is plotted on the vertical axis when you're looking at a speed graph. So you've got distance over time, same thing as the formula. And right here you can see the same thing. So you got distance on the vertical axis, time on the horizontal axis, and then a nice consistent scale for the graph. Okay, 1, 2, 3, so it goes up by steady increments. Okay, could have gone 5, 10, 15, 20. It will all depend on the numbers you're using. Might go up 2, 4, 6, 8, but it must be nice, even scale of numbers on your graph, on your axis. So distance on the vertical, horizontal is time, and then a nice even plot. The main thing is going to be you will be interpreting graphs. So you might see a graph like this and you have to tell me what the situation is that's going on, okay, as well as with making these graphs. So that pretty much sums up section 1. If you'd like to see a summary of section 1, you can look on page 75 in your book. There's also some questions on page 75 that you should take a look at that might help you make sure you understand what was just covered in this podcast and what's covered in section 3.1 in your book.